like in 1D. Okay, we have a chain rule in 1D, one dimensions. So in multiple dimensions, we know how to take composite functions. So let's construct a composite function such that we end up with a single variable, function of single variable. Okay, so take a composite function that is f of t, and we denote it by gt. Function of t and we can construct a function of a single variable like this. Where f is a scalar field. Okay. We map some interval to and g being a composite function. That's R2R. Okay. However, I shouldn't say R here. I would say it's an interval. So symmetry to R. Okay. So if I denote this interval by J, okay, then it will map J to R. So if denote J to be the interval, okay, then modify the respective expressions okay. So here f is completely Rn. We can even restrict it a little bit. We can just say, okay, so there's some subset of Rn. Okay. So then at the end of the day, we will do it in a ball, in a subset of Rn. We don't have to mention it again. So let's be precise from the word go. Okay. So what kind of corresponding physical questions? Sometimes it's good to think of mathematics in terms of physical problems that you're trying to solve. For example, you want to know, you have a solid object which has varying temperature around it, and you want to find the temperature at a particular point. And how do you do it? The question is. Okay. So there is a solid object. Consider the point where you want to find the temperature lies on a curve on the solid object, and along the object temperature varies. Okay. So you construct a function on the curve which gives you the temperature, and as you vary the point on the curve, the temperature of the chain also changes. Okay, this is systematic. Now, our construction is really going in that direction, right? That along a curve, we can actually measure the change of temperature. Okay, that's the way we'll do it. Okay.
So is it J? J.
Yeah, that's J. Pardon my
No.
my J and my T sometimes becomes same.
Is it always to be a closed interval?
It's why, because a curve has a starting point and end point. So you have, okay. If I draw a curve will have a starting point and end point. Then will correspond to the endpoints of the interval. Yeah. Okay. So our GT is composite function GT. So what is, before going to GT, let me just say what R is. R is some, so that curve on the solid is actually the R. Okay, R is a vector valued function, it's a curve, right? So a curve, so physical example, okay, take some solid, that becomes horribly wrong with me. Okay, and suppose it has varying temperature around it. Take a curve on it. Okay, so let f of x gives the temperature on a 3D solid. Okay. It could be any dimensions. Let me generalize it, not in 3D, but ND. It's n dimensional solid. This construction works for all the higher dimensions. Okay, and as the point x varies, okay, fx changes. Yeah. Yeah.
Chain rule for derivatives or scalar fields.
Chain rule, yeah. Maybe. Yeah.
See some difference in this.
Yeah, maybe.
The book goes in a different way.
How?
I don't know. Scalars. Putting the Laplace in.
We will come to that.
Okay.
We haven't really gone to there. We will come to that. We haven't reached the nebulous. We will come. Yeah. We haven't written when we write the derivative, we just define the function. The derivative will give you the.
Oh, okay. Well, now it's the function.
Yeah. Setting the ground. Preparing the ground. Okay, so the question is, okay, let me pose a question. Question is how f of x changes along a curve. Suppose the curve is C, called C, lying in the solid. So to answer this, we already have some construction. So let us redefine these things like R, F, and G in terms of this physical setup. So what would be the R? So R would be, look at the definition of R. R is a vector valued function. So any curve on a solid will be a vector valued function.
So can you go down
Sir.
so I can see the statement that we're trying to answer? How fx changes along a curve C lying in the
Solid.
solid, on the solid, right?
Lying on the solid. Lying on the solid. Lying on the solid.
Could be inside as well.
Yeah. Okay. So R is something which is describing the curve. Okay. Any curve you can think of as a map from some interval to these points which are living in some Rn. Okay. In this case. Okay. So this R is describing a curve. Okay. So here I can just write a curve. It describes a curve. Oops. So okay. So R is a curve. Or is describing a curve, let's say. Describing because describing curve. Or describing the curve C, because we have already mentioned about the curve. Describing the curve C. Okay. And it's a okay. Okay. And the composite, which is GT, okay, measures the temperature as a function of T instead of function of X. Temperature as a function of T. Have I said T before? T is something which is, so here is a T. T is the parameter, and you can consider T as an element of some interval. Okay. So whenever I'm saying this T is some interval. Okay.
So why is T better than X in the coordinates?
It helps us to do the chain rule. And chain rule is
Physically, what is the better? Why is it a superior?
yeah, because we'll see. We'll prove certain things with it to give us the power. We already have the construction in the previous classes.
And physically, I think you might say that, if you think of physical process, then, you're going back to a solid example. The Rn, then, x, y, and z, or x1, x2, xn, they will tell you the coordinates of a point or a curve in a solid, right? But what Abhijeet chooses one coordinate system as the origin. Sorry, I can choose as a different coordinate system, right?
Yeah.
So so for me, x1, x2, x3, will be different. But we can both sort of agree that the beginning of the curve will be parameterized by 0.
Yeah.
And the end of the curve will be parameterized by some of the constituent parts.
Yeah.
Then we can have the variation as independent of the coordinate system as final result. And I think that is I'm just going with the physical motivation.
Yeah. The final result has to be independent. Yeah, that's true. Yeah. It will turn out to be that actually. The chain rule. No, that's fine. That is actually what we're going to get actually. The theorem will exactly give us that physical idea. Yeah. So as I was saying, GT measures temperature as a function of T. There is a computational simplicity here because working with n vectors, n vectors is extremely difficult. But with a single variable is very easy. You don't have to worry about all these other dimensions. Right? That's why the whole construction was constructed in a way. And we actually here another problem we might say, okay, so GT, do I really need to know GT? GT's purpose is we don't have to really know GT. Its purpose is to give us the change. What we really care about is the change of G with respect to T, which is the same as moving along the curve, right? So we'll not actually, so we'll extend the 1D chain rule now we will extend the 1D chain rule, okay, which enables us to compute G prime T without determining GT explicitly. Okay. So that is going to be done with the theorem. So this is the first theorem, and this is, have we met any definition? We have, this is not a definition, this is a construction. So theorem 1. Okay, so this theorem goes by the name of chain rule. This is chain rule of a scalar or for a scalar field. So let F as map from Rn to R is a scalar field, okay, and R is a map from some interval J to Rn, okay, and define G of T as F of R of T, okay. Where T is J is some interval, some closed interval, okay, of R. So generally it becomes 0 or 1, but yeah.
So the question is R has to be defined along the every points in the interval.
Yes.
Continuity, which will continue.
Yeah. I mean, on that interval, it maps every point on the interval to Rn.
Say I have a box.
So you are actually, so that's why the physical example was there. So actually, it's a curve.
Yeah.
So curve is continuous.
Yeah.
It's a continuous curve. Yeah.
Let's say I have an example like say if I remove a point inside the curve. We say there are many physical things like say I don't have to say a box with some internal hollow.
Internal?
Hollow.
Hollow. Okay. Well, then.
Like say in a box.
Yeah, we bring.
We have air inside.
Well, then we will not go through that obviously. So you can still construct some curve when I just going around that hollow, going around it.
Goes through the surface, right?
Yeah.
So we can still construct a curve if we take air inside.
Actually, let's consider it on the surface of the solid.
Yeah.
Okay.
If
Yeah, but then the problem that comes with that when you're in the surface of solid, then you have a dimensional issue. Then you have to address.
Yeah,
solid is a 3D, but the surface is a 2D.
I get the point.
Right? Yeah. So
I get the point because of the way we are defining that it has to be a continuous.
Yeah.
Because the function varies along.
If you have some sort of holes, you can always traverse it, as long as the hole doesn't carry any other sources.
Yeah, like say there are many physical examples.
Yeah.
Like say we are saying it for temperature, but there are many
this
elasticities. There are a lot of problems.
Yeah, that is not the point of this construction. This is just building up, right? This is more complicated examples we can go later. Okay.
I mean, this is just one of the most fundamental constructions. It has, you're right, infinite number of applications. And the way it just motivating one simple physical application. You're right.
Yeah.
It could be, for example, if you're doing machine learning, right? It could be that you have some manifold of parameter space and you are looking at some cost function, and the cost function is a function of the path. You want to minimize the cost function, right? So,
yeah, pretty much, yeah. That's machine learning. To be a point in, say, in the interval at which well, I'm going to switch my notations because there'll be two arrows and a prime. So I'm going to switch. This exists, okay, and f is differentiable scalar field. Right. And G prime T exists. Why G prime T exists? Because f and r are already well defined. Okay. F derivative is well defined, r the derivatives are well defined.
I think I got my answer because for differentiability I need continuity, right? So
Yeah.
I have to consider something.
Yeah.
Yeah.
Okay, well, yeah, that's the most accurate description. And equal to the exists and equal to the dot product. What is the dot product? Dot product is this one. G prime T exists. It exists, and what is this expression? The expression is this. Okay. That's the statement. Let's prove it. So so the reason for calling it A, because I'm going to construct a ball there, and you have already said, okay, but that is going to vary out for all the points on the solid. Let A be that RT and R prime T exists at interval. When it means that every point. Since S is open, okay, so it's some open subset of Rn, so it's open, there's an N ball, an open ball, or open N ball, okay, lying entirely in S.
So
Yeah.
I'm being very picky, but I have a little bit of a problem with that notation. Because you're putting A as R of T, okay?
Right.
Now, the gradient of F,
Right.
in that first factor,
Yeah.
F is a function of R.
No, Rn. It's a scalar field.
Yeah, F is a function of
R. Oh yeah. Okay. Yeah.
Right.
Yeah. Sorry.
It is, yeah, sorry. So, what I'm trying to say is that R is not a function of T.
Right. Right.
So that value of R, I guess, is determined by the T that we choose, right?
Yeah. That's
So,
we start with one particular point. We choose a particular point in the interval. At that point, we find R, that is the point on the solid lying on a curve. And at that point, it's everything happening at that point.
I think it's fine. The notation is good.
Yeah. I understand what you mean. The T is changing, R is changing, so A is
okay. We just have to remember that F is a function of R. We are evaluating R where it is mapped from the that you choose for t.
Right.
Okay, thank you.
I have a question here. My question is, like, say we are defining R in a closed interval. Like,
Right.
the domain is R,
Right.
the R is in a closed interval, so the range is to be in a closed interval,
Right.
right? But when we are putting F, R in F, we are defining it as an open interval. The
Where?
domain of F is open interval, but the range of R is closed.
It's not, well, because of S, it's defined on S.
That means we are taking a larger domain than
Exactly,
R of
exactly,
T.
exactly, yes. That curve is lying in that domain, right.
Larger domain.
Larger domain.
R of T.
Yeah.
And range of R of T.
Yeah. And it's a whole solid. My curve is not going to go through a whole solid. Right? It's a good question. So, take h not equal to 0, small enough. So if h takes h small enough, but which is not equal to 0, okay, small enough such that r of t plus h lies. So yeah, this is small. Okay, so this statement is okay. We can do that. Lies in the ball. A-R. When I said the ball, I should have used the notation here. So there will be some radius which I should not introduce with R. Let me find another variable for the radius. I don't know. Let's call this D or something. Okay. So let y of t, there'll be a lot of lets here. And from here we can see as y tends to 0 vector as our h tends to 0. First of many. All right. So from here we can do something. We can find rt plus h in terms of y. Y of t. So this is, we define this as a, remember? So this is going to be this. This is, yeah, thank you.
A is also vector.
I'm sorry?
Above R.
Above R.
A is also vector.
A is a vector. A is a vector, yeah. Yeah, well, this was a mnemonic. No, A is not a vector. Yeah, because it's actually with T.
So I think here is where, I think the problem with that notation comes in. Is, you're subtracting R in different points. They're quite close to each other.
Right.
So if you call one A, but you don't have a argument of A, then how do you distinguish between the two terms?
Yeah.
And if you do include an argument for A, then why not just take it off?
Well, actually, this is happening. The A is actually the thing here. RT plus is some point which is very close to A.
So you're not saying that RT plus H is A.
So this is what's happening. Suppose this is.
No, I know what's happening.
Yeah.
I'm just
So
talking about
this
the
is.
notation.
Yeah.
The notation is that, A is a fixed point.
Yeah.
Oh,
A is a fixed
rise.
point.
Right. That's okay.
Okay, so we have it. Then what we want to compute is, so before doing the derivative, we have to find the difference. So the difference, g t plus h minus g of t. So what our goal is? Our goal is to find this. And to find this, we have to first find the difference. And this is the difference. and this is written in terms of not yet, yeah, because we have not demanded certain things. It has derivatives in this interval, etc. So we have not demanded them, right? But we have already constructed the composite function. So g of t is our composite function. No, it's given in here, right? So we'll use that. Okay. So using the definition, we can write this. Here I have to be this. So I can call it A R of t, right? And using the definition of g of t. Okay. So that's the difference. Okay. Now I'm going to substitute this result. So let me call this equation call. And for the brevity, I'm dropping the t. Okay. Now, we're not going to use mean value theorem here because we have not demanded that all the partial derivatives exist. When I talked about f, I have to demand that in that region all the partial derivatives exist and other boundary arguments. I have not demanded. Last theorem we said that because we already had those continuous partial derivatives. Okay, even though it would seem like the mean value theorem will give us the same answer if we apply here, but we do not have that luxury of, we do not have a demand basically. Okay, here we will apply because that is differentiable. So what you apply based on what the question says. In the previous theorem, question says we had a collection of partial derivatives. That's why we went to mean value theorem. Here we are given a differentiable function, a scalar field. So we will apply Taylor's theorem.
Doesn't differentiable imply continuous and existence of partial derivatives?
That is also true. But that is a very rounded way. Yeah, that is also true. But that's a very rounded way of going through it. Yes, differentiability is much stronger.
Yeah.
And yeah. So we could not have applied Taylor's theorem in the last, but here we can. Okay.
You said you are going to
Also, even if it's differentiable, you have to demand that all the partial derivatives exist in that interval, and you think you can apply it.
Yeah, because all the directional derivatives exist because of the
Yeah.
So we can expand it and say prove that all the
Yeah.
partial derivatives exist.
Yeah, we can do that as well. Yeah, differentiability is much stronger. However, I'm going to do Taylor because there is one thing needs to be. Is there any problem using? That's a good question. If I use mean value theorem, there is no problem either. There is no problem. I can just go ahead and use mean value theorem. Let me use it. Let's use the mean value theorem here. What is the mean value theorem here?
A prime
A with respect to y, isn't it?
No, there would be there would be. Oh yeah.
But there is a problem here. One problem, yeah, you're right. Here, if I apply it, because g prime 0 is that one, no? It's a plus ty and that. So there is a problem here with the construction because I have to have a t here. So I cannot apply mean value theorem here.
Yeah.
Okay. Right.
Sorry, I missed it.
Yeah.
I couldn't understand why you couldn't apply.
Okay, because the way we derive a mean value theorem with g, okay, had this a plus ty there.
That's TY.
Ty there. Okay. So our expression will not be consistent if you check it. Because g prime 0, what I'm trying to write, so what we found is this. G prime of 0, we found this to be there. This, right?
Yeah.
But here this is,
G of theta.
Yeah.
G of theta rather than F
yeah.
plus.
Well, the thing is that I can still apply mean value theorem, but I will mess up the notations, I guess.
I think we have to define another open interval.
We did it. There we defined g of t to be f of how did we define that one? A plus ty. Didn't we? We defined it this way, no? But here it's not the same. So if we call this h, I don't think there is a problem.
Yeah.
If I call this h, say, I call this h, and the construction goes through, no? Then this would be h prime of 0 would be f of a with respect to y, no? It should go through.
We just need another open interval. That's it.
Yeah, but well, yeah, man, we need some extra, not t, but something else, no?
Yeah.
Let's call it theta.
Like we have used.
Yeah, we can just use this parameter here and just, yeah, we can apply this. It is much.
Yeah.
Instead of using Taylor theorem, we can do this actually. However, the arguments will be a bit involved. And you have to check that mean value theorems are consistent. So you have to come up with all these h's. That's the problem. Taylor theorem doesn't probably require. So I'll do the both. Then we use the mean value here. Okay. But it can be applied. It was probably before the last one, so yeah.
It was before the last class.
Yeah, so okay. So this actually will be the prime here. F prime A with respect to y, which is the same as
I think it's going to be f prime a plus y of theta, because any point between 0 and y, a plus y theta y.
there'll be a theta here.
No.
Which one?
A plus theta y. The expression was a plus a prime a plus theta y.
Theta y.
Yeah. No, not that. A plus theta y.
No, I'm writing f of h prime of 0.
Oh, no.
Not that one. Let me think about it before writing it. Let me think about it. I wanted to apply mean value theorem here. Okay, let's not waste time because I have to cover many things. We'll do in the Slack, or you can do it as a homework. Okay. Let me not.
Oh, I think another issue is like that we haven't defined what the size of the ball is, right? But in mean value theorem, we have defined that. Like say there was a parameter in closed interval t, right?
Yeah.
We're using that, and we used it as the size of the system.
We can do that actually, as long as.
But we are introducing more variables.
No, that is, yeah, but in a sense, yeah.
I think that
Yeah.
is what.
Yeah.
Yeah.
Yeah. Let's see. So this is like an exercise or later? This is another avenue that you can explore. This is a nice avenue. Right. That's what I was talking about. That in that other, so you have to. So if you are given some continuous partial derivatives in a given interval, then you just go ahead and apply mean value theorem. Otherwise, you have to construct them back. But you can construct them. That's the point, right? You can. You can do that. Mean value
We have
theorem.
to introduce two more variables.
Yeah, but that's always can be done as long as conditions are met. So here we do the Taylor expansion, Taylor theorem to the first order, and we had this expression from the Taylor theorem that is Nebva Fa dotted with y plus norm of v e a y. Okay, my y and j might become the same. Okay, this is not a vector. So that's from the Taylor theorem. Okay, good. So far so good. Now here we have to mention where e goes to 0 as norm of v goes to 0. Okay. But why am I writing v here? Sometimes you might like to tell me why is the v here? Why is the v doing here? Should be y, no? which makes sense because we took h to be small, so that we tend h to 0. Okay, h will never be 0, but we tend to 0. Okay. Now what we can do, what further we can do? So we will write what y is now, writing on both sides. So remembering what y is defined by equation call, which is this. So what is y is nothing but r of t plus h. So if you like, you can call a to be r of t again. And okay, not this right now, this, and the rest is just a norm of y times e. Maybe I can squeeze it here somehow. So now I'm going to divide by h on both sides. Okay, and take the limit, take h tends to 0. Okay. What happens, this is g prime t. Okay. This is going to be r prime t, and as h tends to 0, what happens? Let's see what happens to y. Look at our equation call. As h tends to 0, y tends to 0. As y tends to 0, this term drops off. So we have this.
We have plus or minus 1.
Yeah. So what happens is that h, take h, so y mod, as a result, y mod also tends to 0. As a result, e also tends to 0. And drop them and just find the results, what we are looking for. So this will give us a change of temperature along the curve. And as I was saying, this is something which is independent of, this is scalar product, this is independent of the choice of a system.
So what is interesting is it's all reparameterization back.
Exactly.
That if you change your t to a different parameterization, as long as the map between the new and old parameter is 1 to 1, the same quote unquote physical point will give you the same answer.
That's true. Okay, so look at an example. The example is, say, directional derivative along a curve. Okay. So let r of t describe a curve C. R prime of t is the velocity vector. If it's a particle line, it's a velocity vector, or for any line, it will be a tangent vector. Let r prime of t is not equal to the 0 vector. Also letters. So this remark is important because I don't want my tangent vector to be. This is important. Okay, and t be defined by this is the unit tangent vector along C. Then blah. dotted is called the directional derivative of f along curve C. So that's the definition. Now let's do it for a plane curve. So what could be an example of a plane curve? Say there is a curve going like this. Suppose at this point, this is the tangent, suppose. So let me clear the tangent here a little bit better. So alpha, so beta. These are changing with the curve, so they are also functions of t. For a plane curve, say t of has this expression. So it's just, you can use the convince that this is the case. Okay. So you can check its norm is 1. And from this you can easily find the decomposition from the picture. So the directional derivative along the curve, if we compute it here, I'm not with this one somehow. This might become a bit of a problem. So we can use some notations and you can write it. Just gonna write down the final answer. Okay. So this you would write some notation which is d1 of f. Okay. And then you write the next one and then I skipped that one.
Isn't that supposed to be r prime t?
This one.
No.
Oh, yeah, you're right. Here, this is this one. This
Yeah,
has to be.
yeah.
This has to be r prime. Yeah, you're right. Exactly right. No one said that. I'm sorry. It has to be r prime, no, because there's a tangent vector. This is a tangent vector. This is, if I'm defining this to be directional, it has to be the tangent vector of that. Okay. Yeah, exactly. So this is the t. Tangent vector to the curve. Sorry, I got sloppy there. So this concludes our discussion of chain rule. Okay. There's some nice results. Check example 3 from Apostle. Also, example 2 is a nice calculation. Yeah. Example 3 from Apostle and example 2 and 3. 2 is a good calculation and 3 is also some results which are one and the same. Any questions? So now we're going to talk about level sets and tangent planes. Applications to geometry. So this would be. So I skipped a line. This is unnecessary. When if you want to go from this line to this line, you write some middle line. You could write. Okay. For example, the first term could be written as d1 of f, which is the same as writing f. It's kind of fun writing it at the point r with respect to e1.
Another question.
Yeah.
Can you just scroll up? Yeah, I think that's okay. we are replacing the r prime term with t, right? So if we substitute that, don't we have the magnitude of r is?
I'm sorry. Yeah, well, that's another way of expressing it. But we are writing exactly the same thing, no? Of course, these are things.
Oh, you are taking t as unit.
Yeah, it is only the direction along the tangent vector.
Is r also unit?
No.
Then in the previous proof, we have proved that gradient of f time dot product with r rate of change, and here we are replacing that rate of change r
By
inside
unit,
r function with t with this t function. Then my question is that the magnitude of r is missing. I think
no, it's not missing. I'm defining it. It's for any
because
vector.
if we substitute r prime,
Well, I'm completely well. So this is an arbitrary vector. This r and this r doesn't have to be same. I'm not substituting it.
uh,
This r is a proxy for all the vectors.
So these just example like.
Yeah. Okay, so for brevity, okay, so okay, so yeah, there are two different. Okay, this you don't just go in and substitute. This is true for any vector. We're doing it for the unit vector. So I think if you understand that, I don't have to change anything.
yeah, that is
This is true for the unit vector as well. That's why we are calling it directional derivative along a curve. Just the direction. Okay. Okay, so now applications to geometry. Okay. So these will be level sets and tangent planes. Okay. Okay, so chain rule, can be used to deduce geometric properties of the gradient vector. So this chain rule has this nice construction which is more than just finding the rate of change. It's more than replacing f, rate of change of f. It's doing more than that. Much more than that actually. Let's see how. So we define this LC, let x or f of x be a scalar field. Okay, then this is, so scalar field some subset and I'm not writing it again. Maybe I should. Then this is a definition, by the way. So let me put that definition. Definition of a level set. This is definition 1 for the day. The level set of a scalar field f is defined by the following set. Now see all the points belong to S, which is a subset of I, such that C. Okay. Where C is the level of the scalar field. This turns out to be a very rich construction. These ideas are also used in the theory of manifolds in the differential geometry to find many submanifolds. So there is a manifold, and you embedded in that manifold there is a submanifold. So these ideas can be used. Similarly, here we'll see. We'll find Rn there are surfaces. We'll find. So in 3D there are 2D surfaces. In 2D there are curves.
So, for example, the submanifold would be a sphere, and C could be the radius of the sphere, right?
Yeah. Yeah, exactly. That would be also the case. Yeah, we will meet in this. Yeah. So some examples, right? For example, in R2, LC, as I was saying, LC would be a level curve. LC is a level curve. In R3, LC is a level surface. Okay, and it goes on with dimensions. So level curves are also known as contour maps, contour lines. So families of level sets occur in many physical situations. For example, heat flow, electrostatics, to name a few. So for example, if you have, or also in fluid mechanics, fluid flow. So if these are your actually these all of these things goes by the name of potential theory. So this actually goes something called potential theory. So these are a good tool in that theory. So these are isotherms. So isotherms are an example of level set. No? So this is say C1 level, this is C2 level, and this is C3 level. So all the points lying on this curve all the points lying on this curve actually producing C1. The same temperature. That's why they're isotherm. And heat flow are also going to be curves, but those curves are going to have tangents that are perpendicular to the isotherms. So this is say a heat flow, and this curve is orthogonal to those isotherm curves. So heat flow occurs in the rapid change of temperature, in the direction of rapid change of temperature.
So you mean in the direction of maximum change of temperature.
Right. Direction of rapid change, the most rapid, yeah, or maximum change.
Most rapid. Yeah.
I have a question.
Yeah.
Level sets a scalar mapping, right? Let's say
Not necessarily, but
bar.
in this case, it's level set of a scalar field. Very good. Okay. Not necessarily, but yeah.
There is a vector version of this also.
But when I'm talking about manifolds, the map between manifolds, it could be any dimension.
Yeah. Then the heat flow is okay because heat flow itself is a vector.
So in terms of theory, I think
No, but Huh?
Level set is also scalar.
No, it doesn't have to be.
Not the level set, but the level.
But if I map from n to m, of different dimensions, manifolds, then the C is also dependent on what dimension I am. It doesn't have to be. In this case, because it's a scalar field, we are doing a scalar field theory here. That's why it is defined as a. So there are regular level set theorems in manifold, and m could be any dimension. And we have 4 dimensions.
Oh, okay.
Well, there is another way to probably see this.
Because heat flow itself is a vector.
Yeah.
Because that Q, it is a gradient of
Heat flow
temperature.
is a vector.
Heat flow is not. It's not.
Heat because it is gradient of
C is a
temperature.
scalar. So what I'm saying is C is always a scalar.
No, it's a depends. No, in this case, it's a scalar. Here heat flow has nothing to do with level curves. Well, it has. It is orthogonal to level curves, but it is not a level set itself. So, yeah. In this case, it's a scalar because it's for a scalar field. It could be a vector field.
Okay, are you going to define that?
No, I'm not.
Okay. Can you give me a physical example?
I have to think about it. But I can give you some manifold like abstract examples because there are theorems which we know we can apply. When you have to.
By physical example, you can give me an example from differential geometry.
Yeah, example of submanifolds. Regular submanifolds are.
Give me a very particular example.
Well, so you can construct. So what is a regular submanifold? You can prove certain theorems regarding GL, NR, and SLNR using the regular level set theorem. I will give you the references.
No.
SLNR,
I want to get an intuitive picture of what you're trying to say.
Okay.
So, let me just say it in this way. If I imagine a submanifold of a manifold, suppose I take Rn, where n is some large integer,
Yeah.
and I'm looking at a submanifold, right?
Yeah.
So the submanifold would be defined by either one equation or more than one equation.
Yeah. Well, so there are critical.
So I say that when it's more than one equation, more than one constraints, that's when you have a more general level set.
Yeah. So regular. What is a regular point? Let me define it. Then it will become clear. So regular. So there is a map between two manifolds.
Yeah.
Yeah.
So you define discuss manifold.
We haven't. It was just.
Think of them Rn and I. Yeah.
Oh yeah, you can say them. Yeah.
So think of them as that's very important. You should not. But think of them as n as say Rn.
Locally Rn. It would be any curved surface, but locally it is Rn. We are talking about smooth manifolds, by the way.
Well, let's talk. Okay.
Yeah. So if there are no critical points, if there are critical points, it's not regular. If the function has some critical points, the map is not regular. Okay. If it has no critical points, okay, or f inverse of some element of this has no image, then this is called a regular point. Okay. So opposite is true. So I'm considering that no critical points, then its image is going to be a regular value. And if I have a regular value C, then f inverse C is going to lie on the set N. Well, manifold N, right? It's going to lie in manifold N, okay? And with the subspace topology, you can show this actually forms a submanifold in N.
Okay.
So that's an example of a regular level set theorem. So C is your level, so there comes the level set. It's regular because of the definition.
Okay. So let's talk about it.
Yeah, sorry. But the arguments, well, it's just, yeah. We haven't defined critical points in our case. Yeah. Okay. So, So we just discussed about lines of flow as orthogonal to level curves. Now let us construct a level surface. Okay. Let us construct not level surface. Let's say construct. We will construct, but let's construct a tangent plane at a point of a level surface. Let's do that. So let me first draw the diagram here. That's not good. That's even worse. Okay. And suppose take a point here. Point. So let me call this point A. I also say that there is a okay. So consider as let's consider that's a scalar field. Be more precise. Let me do this for R3 is a differentiable scalar field. Okay, let LC be one of its level surface. In the figure, this is the LC. So 3 dimension, this is the LC. Let A be an element of LC, okay, which means it's part of the level surface, okay, and gamma is a curve passing through A. So, sorry, this is the gamma. Okay, so what are we going to do? We are going to prove that nebula of F at the point A is actually orthogonal to some tangent vector at A. This is what we are going to prove. Okay. It's like the goal. I want to prove this. Okay. So let's do it. Let gamma be described. So that's what probably a mathematical way of solving a problem means. You define everything clearly and then you write down. So if you don't start defining anything clearly, a mathematician will just not going to buy it. Gamma be described by a differentiable vector valued function. Okay. since, look at gamma, where gamma lies. Gamma is part of LC, no? Something similar we were talking about when you open something. Gamma is lying on LC.
That's
Yeah. So the yellow one is actually part of LC. Well, there is one thing I did. Yeah. Sorry. I should have completely contained it in LC. Okay. This doesn't have to be in the plane. It's like a so 3D picture.
is that plain LC?
This is LC. I haven't yet arrived to the red stuff.
So let me try to get the geometry straight. LC is the blue
Yes.
surface,
It's the blue surface, yeah, exactly.
and the red surface is a plane.
I haven't yet arrived to it. Yeah, I haven't defined it yet. The point is there.
And but the yellow line, is that in LC?
Yes.
It is contained in LC.
It's contained in LC. Okay. But you can guess what that would be. The surface. You have to guess quite intuitively. Yeah, it will be perpendicular. It will be perpendicular. Yeah. Okay, tangent plane.
It will locally touch LC at one point.
Yeah, exactly. So intuitively that will be the case. Because it's at A, and that's a plane at that point. So you have so this is a surface, and yeah, I could do this one as well. Yeah. So this is like our tangent. So this is a tangent plane, and this is the LC. It's at a particular point. So there is a one point, and there is a plane. So that's the intuitive picture. So if you have intuitive picture, you actually can grasp what we are going without blinding out. I don't think people can do geometry blindly, without really at where I'm heading to. Some thing.
Isn't it like going to the Rn?
Sorry?
J to Rn.
Yes, R3. Because we are doing it specifically in 3 dimensions here. So, yeah, since gamma is an element of LC, okay. Since this is true, so our function, scalar field, this is true, right? Level set, that's how C comes in. This is the definition of level set. So let's look at the definition of level set. This is the definition of level set. So I'm just writing this part now. Okay. Because my points are lying in gamma, you can do this. Because it's true for LC, it should be true for gamma. Because gamma is completely contained in LC. Okay. However, this is true. The important point here is that it is true for all t. Therefore, for all t, this is a constant. So if I take a derivative with respect to t, it's going to be 0. Okay. So now, if I define this gt, then g prime t is 0 actually. And pick t such that, okay, such that r of t equals a. The gamma passes through a. So for every point it is true. So I can pick the t such that I find the point a. So I'm going to call it a 1. So T1 lies in the same j. So it's a particular value of j in the interval. Okay. So
what was A again?
by chain rule. I'm sorry, A is the point. This is the point.
And A, B, L, C, and lambda, gamma be a curve passing through A. So
A.
A is some point on the level set,
Yes.
and gamma is a curve passing through it.
Yes. We haven't yet come to the plane.
Okay. And gamma is being described by a differential function, right?
Yes. Okay. Everything is. Yeah. We are going to construct the. You see, you got a fair amount of work to construct it, but okay. By chain rule. So, by chain rule, what we know is that G prime T, or in this case T1, is nothing but going to be dot. Well, no, sorry. It's T1. Okay. Very good. So this is 0, right?
Yeah.
So what we have been able to show, this is the tangent vector to the curve gamma. Gamma at A. And our gradient is actually orthogonal to it. It's the gradient that's going to help us to nail down the surface.
So we haven't defined what a tangent vector is.
We have.
We have.
This is the tangent vector. So we have a gamma. We have already met what a tangent vector is. So this is a gamma and r prime t, because
So what is gamma?
gamma is the curve.
Okay. So
Yeah.
you can actually, there's the last symbol on the top in the middle place. Okay, that's a pointer symbol. So you can almost tap on that.
This one? Or?
Yeah. And then if you touch the screen with your,
Oh, yeah.
and you can even change the color. If you tap on that again, a long tap,
I
you
see.
can even change that color to have your own laser pointer. So if you're trying to point something on the screen without erasing it,
Yeah, that would be better. Yeah, thank you so much. That's like a life hack now.
that's an iPad hack.
Yeah. So this is A, this is the curve, gamma, and at every point there are tangent vectors that can be constructed from the vector valued function, which describes gamma. So that's what we have been able to show. That the gradient, and this is what we set out to prove, that the gradient will be orthogonal to the tangent vector set E. Now we can repeat this. Fun thing is we can repeat this for any curve now, right? We can repeat this for many other curves passing through the point, right? And for every curve, how many curves can there be? Infinite number of curves. And for every curve, I will find a tangent vector which will be perpendicular to the orthogonal to the gradient. So therefore, all these curves, or in other words, tangent vectors of all these curves, actually that's the correct way of saying it, defines a plane. Okay? So that's what I'm going to write down.
But all the curves has to be in LC, right?
Of course, at the going through A, of course. Yeah. So take a family of curves. That's basically this in our picture. Curves on LC passing through A. Oops. Vector to all these curves are orthogonal to the gradient of the scalar field of that point. Okay. So if the gradient itself is not 0, so to be very precise, the tangent vectors define a plane. So this is what a physicist would say obvious. However, a mathematician would say We have to mention it.
Because there could be the surface could be the surface could contain.
But because the zero vector
isotopes.
is orthogonal to every, so if the nabla is a zero vector, you still have the condition satisfied, but you don't get the plane. Zero vector is orthogonal to every vector, everything vector. So this satisfies the condition, but you do not get a plane. Okay, so there is one loophole to that argument. This cannot be zero. Yeah, but well, you would say why? Okay, but this is important to mention. The tangent vectors define a plane, and the gradient is normal to the plane. It turns out before 1900, mathematicians and physicists are the same. After 1900, mathematics gone through a lot of formulation, more abstract way of writing mathematics. People went through, and then people separated. Before that, the same people did the same kind of stuff.
I think people wanted to put mathematics on solid foundation, right?
Yeah.
And then Hilbert's program came, and then
Erlangen
people
program.
started thinking of what is a Russell, Gödel, and then
Bourbaki.
what's his name? The guy, the strange guy who lived in mountains.
Grothendieck.
So these are all different schools. It's exciting.
Hardly mentioned that mathematics has revolutionized so much in the 19th century.
And
In 20th century, yeah. In 20th century.
there's a comic book about the foundation of mathematics. Really good. It's called Logic Comics, and it's about Bertrand Russell and Gödel, the search for the foundation of mathematics.
Logic comics.
Logic Comics.
Oh, I see.
It's actually pretty good.
Yeah.
Pretty good. It's a fictional account of the discovery of the foundations of mathematics.
We'll look into it shortly. Thank you, sir.
I have it, but it's in Canada somewhere. I have all my books in Canada.
Oh, yeah. Oh, so how are you living without them?
There's this thing called LibGen.
Oh, yeah, obviously. So this is
I have
available.
a huge library, but I left it in Canada in a friend's store, in a friend's attic. So hopefully I'll go back one day soon and bring it back.
Yeah. Okay, so we have this, and okay, so normal to the plane. So what is this plane? Gradient is normal to the plane. This plane has a name. This is the tangent plane. This is called the tangent plane of LC at A. So what Sar and I was discussing about, that this LC was called a regular level set. Instead of just level set, it's a regular level set because it does not contain any critical points. By critical point, we mean the first derivative is not zero. Okay. And this tangent plane is the submanifold, and your whole R3 is the manifold. So this has a dimension, submanifold has a codimension 1 or dimension 2.
Sorry, right. It has dimension 2 in R3. So,
and codimension 1. Yeah, but there you go. It's just a dimension between manifold and submanifold, the differences. It doesn't have anything to do with our discussion, but just a little reference to what we are talking about.
For a moment. Are you discussing a three-dimensional example?
Yes, exactly. Okay, so a plane, now let's come to more general or generic here. A plane through a more general and generic with normal vector n. So the gradient is a normal vector, right? The gradient to a surface is a normal vector, right?
So what do you mean by normal vector?
Which is okay. So yeah, okay, yeah. Okay, I thought it was natural. Also, normal means which is perpendicular to the,
Oh, yes, yes.
and it's a unit and normal. Okay,
Oh, no, it's perfect.
it's perpendicular and
Which
normal.
vector?
A surface, and I'm considering the normal to the surface, a vector which is normal to the surface,
Oh, okay, perpendicular.
perpendicular,
Orthogonal.
orthogonal, and also say its norm is one.
Yeah.
Normal, orthogonal, perpendicular, but local.
Yeah,
Because the surface can be curved.
curved, yeah, but it's,
Okay.
yeah, locally, yeah,
But you see, it's only in 3 directions.
yeah.
You cannot do this in high dimensions. In high dimensions, there's more than one normal.
Yeah, obviously, that's true. Yes, exactly. This construction was here.
Yeah.
So yeah. So I was actually using the word general in the case of tangent vectors going to from the tangent vectors to these things, or going from the level. How to define a plane, not just restricting to level sets. How do you define a plane?
So it's width. Is that width?
Width. Oh yeah, I'm sorry. This is how I write usually. Yeah, width. I'm sorry. Yeah.
So a width
With normal vector n. So this is a general statement, irrespective of the level sets. Okay. So level set discussion was this. It's a construction, but now we are saying that a plane through a point with normal vector n consists of all points in R3 satisfying, so this must be vector, this condition. This is definitely coming from the level sets, but I'm defining a plane now. So that's how one defines a plane. Okay, so if this is a definition for a plane, then therefore tangent plane really falls into that. Therefore, tangent plane at A can be written like that. That is the same thing because it's a normal vector. Okay. So an example would be that if we take Cartesian coordinate system, take this and take A to be this. Okay. Then you find this thing. X vector minus, well, let's say x minus xi. আচ্ছা এভাবে লিখতে গেলে আমার চিন্তা করতে হবে নোটেশন নিয়ে, so I don't want to think about notations right now. So what I'm going to do, I'm going to just write down in plain language what I mean. So that there is no confusion. So however, there is one confusion. I forgot the notation. Okay. So in the meantime, let me think about it. So if I write DIFA, that's summed over there, but well, I can do this. This is possible. Yeah, this is what I was trying to write. I'm sorry. Yeah, these are not second, third. These are derivative, which is no. Second derivative means second derivative would be d1, d2 in our notation. Okay, so what is d1? Remember, d1 of f of a is going to be f a with respect to the unit vector first standard. Second is, these are defined the same.
So d1, d2 are directional derivatives.
These are directional derivatives.
Not the second derivative.
Actually, they are partial derivatives as well. Yeah.
Second derivative would have two factors.
Two factors. Do you have fuel for more? Okay. I'm sorry. This one. Yeah. Well. So what this means is that this means that you have xi minus.
That notation is not.
Okay. 1i. Yeah.
If you choose x1, x2, and x3 instead of y1 and z1.
Yeah, but you want a different notation. Oh, okay. So instead of calling it exactly, you could have called these things A1, A2, A3.
Yeah, that's better. That's better.
Which would be more sensible.
Yeah, right.
Unless you want to be Schwinger and you want to use
No, you don't want to be
confusing things. He did something wrong at times, but okay. He is a famous physicist.
It's more like direct. It's not like cliche. Jacobi had this is famous for being very inconsistent with his notation. The Jacobi polynomial.
Jacobi. Oh yeah. Okay. I didn't know.
One was like a Jacobi law.
Hi, Jacobi. Yeah. Jacobi.
He was German, so it's
Yeah, Asha-san told us a story. So he was a sir, and he went to meet some guy like English name is this, but it's spelled this way.
Vincent.
Yeah. So he went there and asked him for Vincent, and the person was there. He's a Frenchman, and he couldn't understand. He said, "He's not here. Vincent is not here." So I repeatedly asked him, "He's not there." So when he's about to leave after a few minutes, he came.
That's all.
Vashante, yeah, Vashante. So Vashante came, and sir was like, "Here is this. His name is not Vincent."
Denizden gitmeyi de var da bu ben de dalmıyoruz. Fakat ne görüyoruz? They should be there from Paris.
That could also be the case. And এখন তো মডার্ন যুগে তো আসলে yeah. So sorry, could be right. Okay, so derivative of a vector field. So let's start a new thing. Derivative of a vector field. So this is our derivative theory for scalar fields, and most of the constructions will be mimicked. Okay, so this is a straightforward. So vector fields are supposed to be more complicated, but once you know scalar field, the complicated becomes much simpler. So we have a head start now. So it is a straightforward extension of scalar fields. Okay, so I'm using this for the first time, so let me write it down. Vector field. Okay, good. So very good. Okay, now, well, you could have actually d1, d2 to mean ddx squared. I mean, if you want to mix up, then if you don't want. Okay, so let's look at the notation. Now this is Rm, be a vector field. Oh, acha, is that the case? Think about it.
Is it Rn to Rn?
Okay.
R into Rm.
M.
Rm, because of vector field. This is correct. I was thinking of something else. Might have to look into that. Yeah.
It's a straightforward extent with SP.
This theory is extension. Derivative theory
So,
of.
I mean, maybe I didn't follow the definitions properly, but if you are in n-dimensional space, say Rn, I would expect a vector field.
This is a vector field.
In that space, Rn, to have n components.
No, it has m components. Vector field itself has m components because its image is in Rm. So for the scalar, this was.
Okay, right. So I mean, I can understand this. So for example, let's just I have in two-dimensional space. It is hard for me to find a three-dimensional vector that is useful for two-dimensional space. Similarly, if I am in a three-dimensional space, it's hard for me to imagine something useful as a vector which has only two components in two dimensions. So that's what I'm saying, is that my intuitive understanding of a vector field is one in which both sides of this map should have the same dimension. Is that
Well, it's in Rn.
did you get my point?
Yeah, I get your point. Yeah, well, yeah, that's true for. Yeah, this is.
Maybe mathematicians do it differently, but that's what I'm saying.
Yeah, well, but you could have vector fields. You could talk about velocity of fluid flow.
Yeah, which is a three-dimensional. I mean, all the examples I'm thinking about is in
2D plane flow you can talk about, even in 3 dimensions, 2D plane flow, which are.
So, as I said, according to Wikipedia, given a subset S in Rn, a vector field is represented by vector value function
Right.
from S to Rn. So, according to Wikipedia, a vector field in subsets of Euclidean space has this. The index, the dimension on both sides of the arrow is the same.
Same.
Otherwise, it's not exactly a vector field. It's some other map. I wouldn't say it's a vector field. Right?
It's a vector field by definition. Yeah.
Yeah, I don't see that. I don't see how that makes sense as a.
Well, you can construct.
No, I mean, mathematically, it's a kind of fine thing. I can construct something like that. I understand. But I wouldn't call it a vector field. But maybe I also does so.
Well, because he's a mathematician, this is a book.
Yeah, exactly.
So yeah, well.
No, I mean you're right. I mean you can have some yeah.
Yeah, but these are. Yeah. Okay, so let's move on. We can think of something about it. So this is a if. Okay, and
Yes, interior set.
in interior of S, yes, interior of S. A is interior of S, and if Y is an element of Rn, okay, so we can define. We define. This. This. H. Okay, that's straightforward. So, whenever the limit exists. The limit may not exist, so we have to check if the limit exists or not. Okay. So here f prime a y, okay, is a vector in Rm. It's a vector in Rm. Okay. Which really means that it has a lot of components. Okay, so there is a f prime 1, f prime, sorry, prime 2, f prime. Okay. There are many components. Each of them are scalar fields. Well, derivative of scalar field, but they are themselves scalar fields as well. Okay. Let
Each of them are derivatives of scalar field
with
with respect to y.
respect to this
In relation to y.
same thing. Why?
Y.
Yeah.
How?
Because they are also Rn to R, it's Rn to Rn. Yes. Okay. F prime. Okay, so sorry. Fk denote the kth component of F. Hello, I'm busy. Busy. Sure. Okay. Sure. Bye. So sorry. Um, kth component of F. Note that a y exists if Fk prime this exists for each k. Okay, we met this thing, remember? The continuity case. So vector field is continuous if and only if all the components are continuous at the point. Right? So by that extension, you need continuity for the derivative. So all this derivative must exist unless
We're just simply extending that continuity definition.
yes, exactly, yes.
I have a question, John.
Yeah. Because these
in
are
the scalar case, we didn't need the continuity definition for derivative.
no. Why is that? Because we already know a scalar field theory, derivative theory of scalar fields.
Yeah.
All the components are scalar fields. If they are continuous, I know how to find the derivative because of the scalar field theory. That's why I'm saying that if I know all these things, then I can get this. That's the statement here. So that requires no justification. That's not true. The justification is there.
This
Okay.
is bidirectional. If and only if.
Yeah, exactly. The if and only if. Sorry, sometimes I forgot.
Yes.
I haven't mentioned. This means if
And
and only if.
kind of close.
Yeah, right. Yeah. So f prime a y. So what is this? Then I was just writing it here. Now let's write in gory detail. As you are talking about Riaz, right? So which can also be written as much more probably clearly.
Just the derivatives.
Prime, yeah, sorry. So f is differentiable at A, which is interior of the S, if there is a linear transformation
So are
TA,
we going on? How long are we going for? So
maybe 5 or 10 minutes.
okay.
5 minutes, okay, 5 minutes.
5 minutes. I think people.
Yeah, let's do it.
Okay, 5 minutes. So f is differentiable at A if there is a linear transformation. This just borrowing our same old terminology, and then okay, such that right. Okay.
Is this the total derivative volume
For the vector fields. Yes. So that's the first order Taylor formula holds for all V with norm of V less than R for some R greater than 0. Okay. What is that R? That R is the, so you have to consider a ball so that it lies in the ball. Okay. So whenever we write this, it's in a ball.